In the last session, we had in detail discussed the concept of controllability and observability. Hope that was clear to everyone. This session is basically intended to give you a better insight about controllability and observability and its mathematical tests. We have seen that in order to be able to do whatever we want with the given dynamic system, there should be proper actuators for the system. In other words, it should be controllable. If a system has proper set of actuators, then at any point of time, with the help of available information about the states, the system can be made controllable. But even if the sensors provide information and if you don't have proper actuators, then the sensor information becomes useless. Hence, we say that it is inevitable for a system to be controllable that it should have proper actuators. There can be a stage when the system might be controllable and observable, but the model need not be controllable and observable. So, while defining the states, we have seen that any system represented by x dot equal to ax plus bu and y equal to cx plus du will represent a state system with x as its state vector. We can have another set of state vector that represents the same system. It is only essential that the number of state variables of a system need be same. For example, for a third order system, we can have x1, x2, x3 as a set of state vectors. A set of state variables. We can have another set of state variables x1, x2, x3 that represent the same system. Maybe with this x1, x2, x3, the system model need not be controllable, and with this system model or with this system states, the system model may be controllable. While discussing the example of a car, we have seen that if only you have the information about position and velocity, the system car can be controllable. If you have a state variable like temperature, it is not relevant for the dynamics of the system. So, if you form a state model with such irrelevant states, the state model may not be controllable. That is the meaning of the statement. Now, we come to the proper definition of controllability. A system is said to be completely state controllable at any time t equal to t0 if there exists an unconstrained control signal. Unconstrained control signal in the sense an input that can transfer an initial state x of t0 to any final state x of tf. So, it can be at x of t0 at time t0 and it should move to x of tf. It can be any value in a finite amount of time. This should be a finite. This time should be finite. If it takes infinite time, then there is no point in controlling. If every state is controllable, then we say that the entire system is controllable. So, this x will have x1 of t0, x2 of t0, etc. up to xn of t0. Similarly, this will be x1 of tf, x2 of tf, and tf is the final time, xn of tf. Now, we move on to the tests for controllability. There are basically two tests for controllability. One, Gilbert test. How do we know that? This test is basically for checking whether a state model is controllable or not. So, first is Gilbert's test. So, this mathematical methods help us to identify whether a given model is controllable or not. So, there are basically some cases, different cases, some 4 cases for Gilbert test. Case A, when the system is with single input and distinct eigenvalues. So let us assume that we have a state model x dot equal to minus a 0 0, 0 minus b 0, 0 0 minus c. So x1, x2, x3 plus 1 1 1 into u. And let us assume that we have another state model x dot equal to minus a 0 0, 0 minus b 0, 0 0 minus c, x1, x2, x3 plus 1 1 0 into u. I am using the same example that are used in the lecture handouts, so you can refer it at any point of time later. Here the state model x, that is this one, in the diagonal canonical form is having a single column matrix for B, and this is called a decoupled form because all the state eigenvalues are distinct, and we can see that every state, that is x1 dot, x2 dot, x3 dot, every state derivative depends only on that state, that is minus a into x1. These two values are 0, that is why it is called decoupled form. There is no relation for x1 dot with x2 and x3. Similarly, there is no relation for x2 dot with x1 and x3 and x3 dot for x1 and x2. So we can say that this state model is in the decoupled form, and here this state model can be controllable only if all the elements of B matrix are present. Only then all the states can be directly related to the input. So there should be an actuating signal for every state to be controlled here. And here we have another example which gives this element as 0. This shows that the state variable is not controllable. If one of the state variables is not controllable, then the entire system is uncontrollable. So in this example, the first one is completely controllable, whereas the second one is not controllable. So according to Gilbert's test, we can say that a diagonal canonical form will be state controllable only if all the elements of the B matrix are non-zero. Now we move to the next one, that is case 2. System with multiple inputs and distinct eigenvalues. I can take an example like this, like x dot equal to minus a 0 0, 0 minus b 0, 0 0 minus c, x1, x2, x3. So this is again the decoupled form. But the only difference between this and the previous case is, here you have two inputs, u1 and u2, 1 0, 1 1, 0 1. And this is something like the previous case. In the previous video we had taken an example of car in which there are two inputs, that is the steering wheel as well as the brake pedal. There are two inputs. And I take another example just for comparison. X dot is equal to minus a 0 0, 0 minus b 0, 0 0 minus c, x1, x2, x3 plus 0 0, 1 1, 0 1, u1, u2. Here if you consider the first example, we can see that in the first example, for the state x1, it is being controlled by u1 alone. The state x2 is being controlled by both u1 and u2. x3 is being controlled by u2 alone. So in the case for multiple inputs with distinct eigenvalues, if all the elements of a particular row of B matrix are 0, then the system is uncontrollable. So the given state model is completely state controllable if the B matrix does not have any row with all zeros. So here this row is not with all zeros, so it is controllable. This input can be used for controlling the state x1. And in this case this row is with full ones, which means that both the inputs have control. And this row is not with all zeros. So this state is also controllable with U2. But if you come to this case, you can see that this row is full of zeros, which means x1 state cannot be controlled with either U1 or U2. So this shows that for multiple input systems, it is essential that the B matrix should not have any row with all zeros. There should be at least one input that can control the state variable. Now we move to the next case. That is case 3. It is single input with repeated eigenvalues. So let us take similarly as in the previous case 2 examples. X dot equal to minus a1 0 minus a 0 0 0 0 minus c. Hope you all remember this case for with Jordan canonical form where you have repeated eigenvalues. So you will have a Jordan block like this, and the matrices can be, the B matrix can be 0 1 1 into U 1 U2. And we can take another example with x dot is equal to minus a 1 0 0 minus a 0 0 0 minus c x 1 0 1 u1. So according to Gilbert's test, for a case with single input with repeated eigenvalues, the necessary and sufficient condition for complete state controllability is that the element of B matrix, that is here, that correspond to the last row of the Jordan block should be non-zero. Because if you consider this Jordan block, you can see that x1 dot depends on both x1 and x2, whereas x2 dot depends only on x2. So this variable variation can be affected only with x2 alone. Here I can write it as x1, x2, x3. So this variable variation is affected only by x2. So it means that there should be some way by which this can be controlled with the help of some input. Whereas this state variation is affected by both x1 and x2. So a change in x2 will naturally affect x1 dot, because if you look at the equation of x1 dot, it is very clear, minus a x1 plus x2, and x2 dot equal to minus a x2 plus this you have only one input. Plus U1. So I can change U1 and I can affect I can make a change in x2. So if x2 is changed, naturally x1 can be changed. x1 dot means the change in x1. So a change in x1 can be affected by changing x2, and that is obtained by a change in U1. So if this element is not present, then we can say that x2 is not affected and x1 dot is also not affected. And coming to this example, here we can say that there is a value here, which means if you write the equation for this one, x1 dot is equal to minus a x1 plus x2 plus u1, and if you look at x2 dot, I can say minus a x2 alone. So u1 I can change the input and make changes in x1, but this will not be reflected in x2 because there is no element here, and hence it is said that the element of the B matrix corresponding to the last row of the Jordan block should be non-zero. Now we move to the next case, that is case 4. Systems with multiple inputs and repeated eigenvalues. So here I take an example like x dot is equal to minus a 1, 0 minus a 0, 0, 0, 0 minus c, x1, x2, x3 plus 0, 0, 1, 0, 0, 1, u1, u2. So here in this case, the state model will have multiple columns for B matrix. The necessary and sufficient condition for complete state controllability is that a row of B matrix corresponding to the last row of the Jordan block should not be with all zeros. So here, just like the previous case, we need to consider only the element corresponding or the row corresponding to the last row of the Jordan block. Here the Jordan block is this one, the last row need to be considered. So the elements correspond in B matrix corresponding to the last row of the Jordan block should not be with all zeros. In that case, the state variable cannot be affected by both input and both the inputs or either one of the inputs. So let us take this example and see whether this is controllable or not. Think for a while and find the answer. This system model is not controllable because this row is full of zeros. That is the element corresponding to the last row of Jordan block. Hope this is clear now. Now we move on to the next one, that is Kuhlman's test. It's a very simple technique. We need to just check the rank of a matrix, that is the controllability matrix. So we have already seen this matrix, controllability matrix, in similarity transformations. For any state model x dot equal to ax plus bu, a controllability matrix of this form can be formed, and the rank of this matrix S matrix should be full. Full rank in the sense it should be the rank should be the same as that of the order of this A matrix. How do you identify the rank of the matrix? Suppose you have a matrix S, then the rank can be identified, or the rank can be said to be full rank provided the determinant of this matrix is non-zero. You just identify the determinant of this matrix, it should be non-zero. If you have determinant as 0, then it says that the rank is not the highest one. So if this is a 3 by 3 matrix and if the determinant is non-zero, the rank is 3. and if the determinant is 0, then the rank could be 2 or 1. Rank is nothing but the order of the largest square matrix whose determinant is non-zero that can be identified from the given matrix. Thank you.